Okay, there, we're recording. So let's get started. And before we do that, I'll just remind you of the schedule. So we met with cohort A this week. Any students who are in cohort A, Mr. Mayer, Ms. Herring, and the lab went exceedingly well. We went over all the safety protocols and the new requirements for PPE for me and for you, so for instructors and for students alike, with having to wear masks and everything. And so if you're in cohort B, we'll be meeting on the 17th of September. And also, this is just a reminder that if you're in cohort A, that this assignment, the refresher lab skills and spectral worksheet, that is due 1 week from yesterday. Yesterday was September 3rd, and so it will be due on September 10th. And it will be an online submission. And so the way you submit that is you go into our class's Canvas page, you click on assignments. After you click on assignments, you scroll down, you find the refresher lab skills and spectral worksheet. You click on that, and then you upload your document. Now, we want you to submit this as a PDF or a Word file. I would prefer a PDF, and it should be completely collated. That means all of the pages should be in one document. We don't want to have to grade 6 or 7 pages. That gets really frustrating and actually very difficult. It certainly adds a layer of complexity to grading when students don't put all of their pages together in one single file, okay? And I'll post some instructions with respect to that on Canvas in the near future. But let's get to the task at hand, which is looking at this spectroscopy practice. So first, we're going to start out just by looking at some spectroscopy practice. There's some stereochemistry practice. If we have time, we might take a look at a couple of those. But I think the most pertinent part will be the first part. And of course, I will post the solutions to that. Let me remind you, again, I'm getting a lot of repeat questions from students that this is not for any value. This is for your own personal edification. I came up with these problems. And so this is for just for practice purposes. All right. Well, let's see here. You can see that it says each of these problems are given an IR and an NMR and a molecular formula. Using this information, determine the structure. The best approach is the following. And I'm not going to read through the entire thing, but you can see that in number 1, it recommends that we calculate the HDI. And the formula for HDI was 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens. And that's a formula you would have seen in Organic Chemistry 1. Then it says to look at the IR absorption bands, NMR signals. And just as a reminder, if you have your Schafstall book handy, so in the Schafstall textbook, Schafstall text, okay, if you're looking for NMR tables, so if you're looking for NMR tables, they are found on page 129. If you're looking for the carbon-13 NMR tables, those are found on page 144. And for the IR tables, those are found on page 115. And I'm sure that you have a lot of chemical shifts and a lot of signals memorized from Organic Chemistry 1 and Organic Chemistry Lab 1. So let's keep those things in mind as we move forward, and let's take a look at the first compound. So I'm going to have to leave it this size, I guess. Hopefully it'll all fit on the screen like that. We're given a molecular formula. You can see we have a beautiful IR here, and we also have some, we have a proton NMR here. So again, our IR, we have our proton NMR here. And I think the first thing that we should do is calculate the HDI of the compound of interest. And so has anybody gone ahead and been able to calculate the HDI yet? Could anybody tell me what the HDI for this compound is? Anyone? Can you hear me? Okay, a couple people say 1. Yes, absolutely. It has an HDI of 1. Okay, is there anything that you see that's of interest in the infrared spectrum? Is there anything there that looks interesting to you? Is there anything of interest in the infrared spectrum? Yeah, exactly. We see a strong absorbance here. It's kind of hard for me to read that. I think I need a new prescription, but it looks to me like it's around 17, 18, something like that, reciprocal centimeters here. And so that indicates that we have a carbonyl stretch from a ketone. A ketone, generally speaking, the carbonyl stretch comes out at around 1715. And so we have our carbonyl stretch here. I don't see anything else of immediate interest here. The only thing that kind of sticks out to me is here, which is the ubiquitous sp3 hybridized carbon hydrogen stretching here. It's not aromatic, and we know that because it doesn't have a high enough HDI. There's no alcohol, there's no amine, there's no nitrogen, and so this compound is going to be a ketone. How do I know that? I know that because I have a carbonyl. Without a doubt, there's a carbonyl in the compound, right? It has an HDI of 1, and so the only unit of unsaturation is found in that carbonyl. Okay, is found there. So that means that it must be a ketone. I don't have the aldehydic CH stretching at 2750 and 2850. And again, we know that this compound must be a ketone. No, it's a ketone, and it has a total of 5 carbons. There really aren't that many possibilities. Okay, there aren't that many possibilities. But let's take a look at the Proton Nmr. Right now, you can see that we have a triplet that integrates for 3 protons. We have 1, 2, 3, 4, 5, 6. We have a sextet that integrates for 2 protons. We have a singlet that integrates for 3 protons, and then we have a triplet that integrates for 2 protons. Okay, so let's see. It's kind of difficult for me to just throw it out there to my students because we haven't covered ketone nomenclature yet, but is there anybody who has an idea of how we might put this together based off of what we're seeing in the proton? The proton is going to tell us what the connectivity of this ketone must be. Okay, if not, I would say that the only way to put this together, okay, if we think about this really hard, we have a singlet that integrates for 3 protons, right? And it has a chemical shift of around 2.1, a little higher than 2.1. That tells me that we must have a methyl ketone, right? Because there's no way that I could get a singlet that integrates for 3 protons unless it was a methyl ketone. Also, what's the base chemical shift of a methyl group? It's 0.9 parts per million, but when it's alpha to a ketone, we add 1 part per million. And so we have 0.9 parts per million plus 1 part per million, and we end up with a total of 1.9, which is close enough to 2. But that's pretty close to the chemical shift that we see right here. It's around 2.1. And so that seems totally reasonable. Right now we have 3 carbons left over, and we have this triplet, we have another triplet, and we have a sextet. Does anybody have an idea of how we might put that together? If you're unsure, I can help you out. There's literally only 2 possibilities for connecting these. They can either all be connected in a row like this, or the compound, the other 3 carbons could be connected like this. This group shown right here, this is an isopropyl group. Okay, an isopropyl group, you should remember that the 2 methyl groups are chemically equivalent, and they both couple to this methyne hydrogen. Therefore, those 6 protons would give you a doublet. So we would see a doublet here. And for this methyne proton, we have 6 plus 1 using our n plus 1 rule. And so we would see a septet for that. And that's something that we covered last spring. If you were in my organic chemistry class last spring, we talked about the isopropyl group. And in here, there is no doublet and there is no septet. We don't see that anywhere. And so that is impossible. It cannot be this structure that I have drawn here. Now let's analyze the 3 carbons that are shown here. What kind of splitting would we see for those protons? Well, again, if we look at the methyl group here, this would be a singlet because it is coupled to no protons. This methylene here is coupled next to these 2 protons. So if I take my n plus 1 rule, 2 plus 1 gives me 3. And so this methylene must give me a triplet. If I look at this methylene right here, it's coupled next to 1, 2, 3, 4, 5 protons. And so again, employing the n plus 1 rule, 5 plus 1 gives me 6, and that would be my sextet. The last methyl group over here is coupled next to these 2 protons of the methylene, and so that would also give me a triplet. Now it's starting to make more sense because in our molecule we have a singlet, we have a singlet in our NMR. We have 2 triplets, we have 2 triplets in our NMR, and we have a sextet, and look it, we have a sextet in our NMR. So now the last thing we're going to do is we're going to annotate this spectrum. And the way that we annotate a proton NMR spectrum is we start on the far right and we label each signal with a letter of the alphabet. So we're going to label our triplet here, A, going down the alphabet, B for our sextet, C for our singlet, and D for our triplet. Now let's redraw the ketone. And we will put the letter next to the hydrogen that is responsible for the signal. I think C is pretty easy because it's the only one that could produce a singlet. So that is C. A is a triplet and D is a triplet. Well, the triplet that is resultant in this blue circle that I have shown here, that triplet is going to be much more deshielded, right? We're going to have a base chemical shift for a methylene of around 1.2. And then we're going to add 1 to that because it's alpha to a carbonyl, which gives us around 2.2. And look, it's just a little more deshielded. Okay, it comes up a little higher than 2.2. And so that makes sense that this would be D. A is very shielded, and that's why its chemical shift is so low. Okay, it's very far away. And if we look at the sextet here, it has to be this. And if we analyze the chemical shift, again, the baseline of a methylene is 1.2 parts per million. And remember, we're going to add 1/5 of the effect of that carbonyl. Now, normally that carbonyl has an effect of de-shielding by 1 part per million, or a chemical shift. It's going to cause the chemical shift to be further downfield by 1 part per million. And so we're going to add 0.2 parts per million, and we get 1.4 parts per million, like that. All right. Give me a thumbs up if you follow me on that one. You don't understand. All right. Dr. Diaz is thoroughly confused. He's like, I don't have an effing clue what you're talking about. All right. Well, let's move on to another problem, and let's see if we can get our strengthen our spectroscopy skills here, and let's give this one a shot. So we have our molecular formula, C4H10O. We have an infrared spectrum, and then we also have an NMR down at the bottom. So we have our IR, and we have our proton NMR. Okay. And the first thing that we're going to do here is we're going to calculate our HDI. Right? That's where I would start. That'll give us a big clue about what kind of functionality we might find in this compound. So our HDI, does anybody have the HDI for this one calculated? Anybody have an idea about the HDI for this one? 0. Thanks, Winona. Yes, there are zero units of unsaturation. I'll throw this one up to you guys too. Is there anything kind of interesting that comes to your attention in the infrared spectrum? Somebody says 3,300. So if I look here around 3,300, yeah, somewhere around here, we see that we have a very broad signal here. Broad signal. Anybody tell me? Yes, absolutely. This is the oxygen-hydrogen stretch, okay, from an alcohol. Okay, so we have an alcohol, and that is where that oxygen is. So if we have an HDI of 0 and 1 oxygen in our compound, there's literally 2 options. It could either be an alcohol or an ether. And we know for certain, just by looking at our infrared spectrum, that it is definitely an alcohol. So right away, we've determined that we have an alcohol. All right. We don't know anything else. There's no other information we can really get from this spectrum except, you know, the ubiquitous sp3 carbon-hydrogen stretch, which I wouldn't give you points for anyway. It shows up in virtually every spectrum we ever look at. But we know it's an alcohol, and now we have a beautiful NMR spectrum to look at. What do we have here? I'll just draw your attention to this and see if anybody can tell me if there's something that's interesting here. Is there anything interesting here in the proton? Absolutely. Thanks, Diego. Yes, we have a septet, right? This is a septet, and then we have a doublet here. So that means we probably have an isopropyl group. Well, the compound only has, the compound only has, where am I? Only has 4 carbons, C4H10O. Okay, so let's keep that in mind. If the compound is C4H10O and it has an isopropyl, then the other carbon has to come off of here, right? And then where could it be? Literally, the only place it could go is right here. You can basically solve this one by process of elimination. Okay. Now what we need to do is we need to annotate the spectrum. So we're going to start on the far right. We're going to label our doublet A, our septet B. This doublet will be C, and this singlet will be D. All right, well, we already covered the isopropyl group, and I explained why the 2 methyl groups shown right here, why those all couple to this methine, 1 hydrogen, okay? So 1 plus 1 gives us 2. And so these methyl groups are the A protons. If I go to my septet B, I have 1, 2, 3, 4, 5, 6, 7, yeah. So the septet is, yeah, it's 7. Anyhow, it's going to be B. Now, some of you might be asking, well, shouldn't it also couple to these 2 protons? Shouldn't it be 6 plus 2, so 8? Shouldn't it give me a non-net or something like that? Generally speaking, once you get past the septet, you won't see any more splitting. You probably could if you did some kind of, you know, special experiment or something, but we don't see that. So there's our septet. Now, between D and C, I'm going to ask you, which one do you think is the alcohol signal? Do you think it's D or C, the alcohol hydrogen? The alcohol hydrogen. Yeah, it's D, right? It's going to be D because that's always going to give you a singlet, right? Alcohols produce singlets, okay? And the reason why is because of B2O exchange, right? Because they exchange with protons in the solvent, and the exchange is so rapid that it's faster than the coupling, and so we don't see any splitting for an alcohol hydrogen. Also, if we look at C, C is 2 protons, right, which are coupled next to 1 proton of the methine. 1 plus 1 gives you 2, and there's our doublet. Give me a thumbs up if that helps, or let me know if you have any questions. That one helped. It's 2 methyl, 1 propanol. be this compound, 2-methyl 1-phenol. All right. Does this help anybody? All right. Okay, slowly coming back. All right, well, let's keep going. And we'll try question number 3. I'm going to give you a few minutes to look at this problem. Take a look at this problem. Does anybody have any ideas about this one? There are only 4 carbons. Not a lot of options. Anybody have any ideas? Functional groups, HDI, anything? Somebody says an aldehyde, maybe? Somebody says HDI of 1. Let's write that down. Okay, so we know that the HDI is 1. All right. And we have 2 oxygens in here. So what are our options? I mean, we could have 2 alcohols, but it's not an alcohol. Not an alcohol. Alcohol. Not a carboxylic acid. What else? It's not an alkene, right? Because we don't have sp2 carbon-hydrogen stretching. But we do have a strong signal here, right, at around 1740. Okay, I think that's what it says, 1743 or something. So this would be a carbonyl stretch. Now there's another really strong stretch down here, which is around 1283, something like that. Okay. Now, whenever you have a stretch that pronounced, sorry, I don't know if I was muted. Anyway. Can you all see my screen with the 4 yellow circles on it around all the esters? Okay, cool, great. So these are really our only possibilities. Now, does anybody, and I'm going to erase all of them, does anybody notice anything interesting in the proton? You know, any conclusions that they could draw from the proton NMR? Anybody notice anything interesting about the proton? Are there any groups in there that might look interesting? If I have a quartet that integrates for 2 protons and a triplet that integrates for 3 protons, does that make anybody think of anything? Yeah, exactly. It must be an ethyl group. Right, so that means we've got to have an ethyl, and then we have a singlet that integrates for 3 protons, and so this must be a methyl. So that means we have a methyl and an ethyl. Okay, well then we literally now narrow it down to 2 options. Right, we have an ester. We can either have our ethyl on this side and our methyl on this side, or our ethyl over here and our methyl over here. It's got to be one of these 2 esters. All right. Can anybody tell me if I call this one A and I call this one B? Could anybody tell me which one it probably is? Yeah, I'd say it's B as well, Diego. And the reason that it's B is based off of what? Chemical shifts. Right. So let's take a look at the chemical shifts of B. And I'm going to erase, or I'll move this one out of the way. Okay. Move that up here. Yes. Right here. All right, let's think about the chemical shifts. The baseline for a methyl was 0.9 parts per million. But when it's next to the oxygen of an ester, we add 3.0 ppm. That gives us 3.9 ppm. And you can see that we're around 3.7. So that's pretty darn close, right? Okay. If we look at this methylene right here, okay, and that is the only one that's going to integrate for 2 protons, well, what's the baseline of a methylene? It's 1.2 parts per million. And then we're going to add 1 part per million to that because of the deshielding effect of the carbonyl group. That gives us a total of 2.2 parts per million. All right. And you can see that we're around 2.1, 2.2, 2.3, maybe 2.35. But that, again, that's very close. If we look at this methyl group, again, our baseline for a methyl is 0.9 parts per million. And then we add 1/5 of that deshielding effect. So we add 0.2 parts per million, which gives us a total of 1.1 parts per million. Remember, these are just approximations. But look, we have 1.1. Look, it's almost exactly at 1.1 parts per million. And so this must be the correct answer, this ester that we've drawn here. So this is called methylpropionate. And now we will annotate the spectrum. And we will start by putting letters on the spectrum. A, starting on the right. B, for this quartet. And C, for this singlet. We will redraw the compound. All right. Okay. Now we will annotate. So A must be the methyl group that is the least deshielded. C would be the methyl group that produces a highly deshielded singlet. And then B would be this methylene because it produces a quartet. And again, that's because it's coupled next to 1, 2, 3 protons here. If you're unsure about the multiplicity of these signals, make sure you revisit the N+1 rule. Okay, that is found in chapter 15 of Klein. Okay, it is also found in the technique section of Schafstall. Okay, let's take a look at another one. Question number 4. C5H10O2. I'll give you a few minutes to take a look at that one. See if you can come up with a structure. Does anybody have any ideas about what the structure might be, or anything they want to share about the IR or the proton or the HDI? Somebody says a ketone. I don't know where they're writing that. Okay, Eric says a ketone. Well, there's definitely a carbonyl group. I agree with you on that. There's certainly a carbonyl stretch. Yeah, we have that. Yep. But what are the possibilities if we have 2 oxygens? Oh, an ester, I mean. Okay. Well, I think that might be a better idea because we also have a strong single carbon-oxygen stretch down here. It's at around 1192. That carbon-oxygen stretch for an ester is usually in the neighborhood of 1,300 to 1,000 reciprocal centimeters, anywhere in there, and it's usually very strong as well. Yeah, I'd say we probably have an ester, and we got esters on the brain today. So it's probably an ester. All right. I mean, you see an oxygen in the formula. What other functional group could it be? It could be a carboxylic acid or an alcohol, but it's definitely not that. Right? There's no indication that we have any oxygen-hydrogen stretching. It could be an ether, but we have a carbonyl here, so we definitely don't just have an ether. That's impossible. Okay, and so I'd say the ester is probably our best bet, and also the HDI for this compound is 1, and so that would take care of the HDI, right? Because there's a double bond in the ester. Now, this is an ester with 5 carbons. Again, I mean, you can start messing around with it like this. 1, 2, 3, 4. Right? 1, 2, 3, 4, 5. There. It could be this. Let's see. 1, 2. You know, I could have one here. 1, 2, 3, 4, 5. Could it be that, right? So that's the kind of approach you want to take. You just want to start thinking about, you know, maybe it could be these esters. It's neither of those. But a better way of doing it, rather than just process of elimination and drawing everything under the sun, would be to examine the NMR. Is there anything that anybody notices about the NMR that, you know, might shed some light on what the structure of this ester would be? Anything that anybody notices in the proton NMR? We have some triplets that integrate for 3 protons and 2 quartets that integrate for 2 protons. We saw this earlier today. Yeah, Diego says 2 ethyl groups. Right, exactly. So we probably have 2 ethyl groups. Ethyl groups. Right, that would mean we'd have one over here, and we'd have one over here. like that. Now let me just move down a little bit here, and let's see if that makes sense. Okay, so I'll redraw the structure. This ester would be called ethyl propanoate or ethyl propionate. All right. Now, does this seem reasonable? Well, if you think about what the multiplicity of this methyl group should be, I'll highlight it in green. This methyl group should be a triplet. The methyl group over here on the far right, that should also be a triplet. Why? Because they're both coupled next to CH2s or methylenes. CH2s have 2 hydrogens. 2 plus 1 gives you 3, and plus 1 rule. So we have 2 triplets. And then if you look at the 2 methylenes, for the exact same reason, both of them should produce quartets, right? Because they're both coupled to 3 protons. And so we have a quartet here and a quartet here. Okay. Now it's just a matter of annotating the compound, the spectrum. So we have A, B, C, D. These are our 4 signals in this compound. Let's redraw the compound again. Well, I think the one that's the most abundantly clear would be D, in my opinion, because you remember that the baseline for a methylene is 1.2 parts per million, but when it's next to the oxygen of an ester, we add 3 parts per million. So that would give us 4.2 parts per million. Again, this is just an approximation, but you can see that we're almost at 4.2. That means that this quartet here has to be these protons here. It's the only possibility. You can check that if you want, right? You can say, okay, the baseline of a methylene is 1.2 parts per million. I'm going to add 1 part per million because it's adjacent or next to a carbonyl group. That would give me 2.2 parts per million. Again, this is just an approximation. And looky, we get 2.2, that's pretty close to me. Okay, so that seems reasonable. Now we have to figure out B and A. Okay, we got to figure out B and A. Well, you can see that with B, it is more de-shielded. So which one of these is going to be more de-shielded? Well, could anybody tell me? Well, if I highlight this one in yellow and if I highlight this one in green, could anybody tell me which one of these methyls would be more de-shielded? Would it be the yellow one or the green one? No, it's not going to be the yellow one. In fact, it's going to be the green one, okay? And the reason why is because the effect of being next to an oxygen of an ester is a de-shielding of 3 parts per million. When you're 1 carbon away from that, you take 1/5 of that. What's 1/5 of 3? Right? 3 divided by 5 is 0.6. That means it's going to have a higher de-shielding effect, right, than being beta over here, in which you'd only add 0.2 because you're beta from a carbonyl. Anyhow, here we go. And so this is going to be our B. Oops, this will be our B protons, and these will be our A protons. All right, I think that's enough of the proton. I will post the solutions to questions 5, 6, and 7. I'll publish just a PDF of the answers and the solutions. And so let's switch gears and let's take a look at some stereochemistry practice. Later on, we're going to do a little dry lab that involves some stereochemistry practice. Around the time of the benzyl reduction, we're also going to put a stereochemistry exercise in there. And so let's switch gears and take a look at this. And if you start with the first question, question 8, it says identify the asymmetric carbons. So asymmetric is the same thing as saying chiral carbons, okay? Or saying a stereocenter. So chiral is the same thing, chiral, stereocenter, okay, whatever. They all are synonymous. Identify the asymmetric carbons, if there are any, in each of the following molecules. I'll throw it out to you guys. Could anybody tell me in the first compound, A, are there any stereocenters in that molecule? If so, how many? 0, 1, 2, 3, 4. Diego says 2. Got it right off the bat. Good. There are 2 stereocenters in this compound. All right, so if we take a look, and if I just draw the bond line structure of this compound, 1, 2, 3, like this, I have a chlorine here and a chlorine here. Sometimes it's a knee-jerk reaction for students to think, well, couldn't I adjust these stereocenters so that I'd have a meso compound? Yes, you certainly could. But remember, meso compounds do contain stereocenters, okay? They just have a plane of symmetry, which cancels out or negates their ability to rotate plane polarized light overall, because the 2 stereocenters, they'll both rotate plane polarized light in equal and opposite amounts, which so will give you a net result of no rotation. Okay, anyhow, where are the 2 stereocenters? I have a stereocenter here and a stereocenter here. Let's look at the first one, and I'll prove it to you that that's a stereocenter. That carbon, if I highlight it in green, let's say, what's it attached to? It's attached to a hydrogen. It's attached to this methyl group. It's attached to the chlorine, and it's also attached to all of this over here. And so it is clearly attached to 4 distinct groups. Remember, for a stereocenter, it must be attached to 4 distinct groups, not 4 distinct atoms, 4 distinct groups. So that leaves us with these 2 carbons, both being stereocenters, this one here and this one here. Let's move on to B. I'll throw it out to you guys. How many stereocenters are there in B? I think this one's maybe an order of magnitude simpler. Somebody says 1. Absolutely. There's a couple people say 1. Yeah, there's only 1 stereocenter in this molecule, and it's the one that I put the red star by. If you look at these other carbons, they're all methylenes, CH2, and by definition, it's impossible for a methylene to be a stereocenter. Why? Because a carbon that is a methylene has 2 hydrogens attached to it. When you have 2 groups or 2 atoms that are identical, it cannot be a stereocenter. And so we have 1 stereocenter. The same rationale applies for a methyl group. A methyl group could never be a stereocenter because it's attached to 3 groups that are alike. All right. Well, with that in mind, let's take a look at C. We'll do this one quickly. How many stereocenters in C? Absolutely, there's none. Big 0, right? There's no. This is an achiral molecule. Achiral, okay? No stereocenters in here. Sometimes it's a knee-jerk reaction for students to say, well, what about this one? Remember, the path going this way, okay, and the path going this way are identical, okay? And so there are no stereocenters in that molecule. All right, let's move on to Cahn-Ingold pre-log rules. And we'll start by looking at this compound here. This is 2-bromobutane, and we need to determine, is this R or S? I'll just throw it out there to my students, see if anybody can get the answer right away. Anybody have an answer for this one? Somebody says S. Yes, Andrew and Diego both say S. I think you're on the right track, right? Remember the Cahn-Ingold pre-log rules. We're interested in this carbon, which is the stereocenter. We have a hydrogen in back here. Now, if we analyze the groups, bromine certainly has the highest atomic number. The hydrogen is going to have the lowest atomic number. Then if I compare straight carbon chains, the longer the chain is always going to have a higher priority, right? Because this carbon is attached to what? It's attached to hydrogen, 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 whereas this carbon over here is attached to carbon, hydrogen, hydrogen. There is my tiebreaker right there. And so that means that the second highest priority group is going to be right here, and this will be 3rd. If I follow that around, it goes from 1 to 2 to 3, like that. That's counterclockwise, and so the stereochemical designation is S. Let's give this one a try here. I'll walk you through this one. Again, we have our stereocenter and our hydrogen it's in the back. That's always a good thing because it makes solving the problem a little bit easier. You can clearly see that bromine has the highest atomic number. It has 35 protons in its nucleus. Am I numbering them in the wrong order? I think I am. Mr. Deon is tired. All right, there we go. Okay, if I look at this carbon here, this is attached to a carbon, hydrogen, hydrogen, and this one here is attached to an oxygen, hydrogen, hydrogen. Oxygen has a higher atomic number than carbon, so that's my tiebreaker, and so this will be the second highest priority group. This will be third. I go from 1 to 2 to 3, like that, which is counterclockwise, and so the stereochemical designation here is S. Let's try one that's maybe a little bit more interesting. This one over here. Okay, I'll give you a second and just see if anybody can come up with an idea for this one. We only have two choices, R or S. Anybody have an idea about this one? This R or S? Yeah, Andrew says R. I think I agree with him. Let's take a little look at the stereocenter. We have our hydrogen in the back. It is definitely going to be the lowest priority. The oxygen will be the first priority. If we look at this carbon here and this carbon here, let's compare the two. The carbon on the right is attached to carbon, carbon, and hydrogen. And the carbon on the left is attached to carbon, hydrogen, and hydrogen. Here is our tiebreaker. And so this group, the isopropyl group, is going to be second priority, and the butyl group will be the third priority. If we follow that around, going from 1 to 2 to 3 like that, that's going clockwise. And so the stereochemical designation is R. Let's try one that's quite a bit more complicated, okay? We can do this one here. There are a couple of ways you can approach this problem, okay? There are a few possibilities. What I like to do myself, if I was solving this problem alone, okay, what I would do is I would imagine that I'm looking down at the molecule this way, okay? No, I'm not looking up. I'm looking at the molecule, okay? Okay, I'm looking down towards this carbon. And what do I see when I look down, right? When I look down, I'm going to see the amino group down here, right? I'm going to see the methyl group up here, and then I'm going to see the vinyl group up here. Okay, so then very clearly you can see that it goes from 1 to 2 to 3, right? It's going in that direction, which is clockwise, and so it's R. Okay, so this is an R stereocenter. That's one way of doing it. And you're like, well, how could you do that? Well, I know that the proton is in the back, right? When I look at the molecule that way. That's one way, and I'm sure that some students use that way. Another way would be to swap two of the groups so that we get the hydrogen in the back. And when we swap two groups, what we do is we would swap the stereochemistry, right? If it's R, it becomes S. If it's S, it becomes R. If you're unsure of what I mean, let me demonstrate. We'll start by redrawing the molecule like this. We're going to put our methyl group out here, okay? And then we're going to put our hydrogen where we want it in the back, and we're going to leave our amino group. So whatever we read as the stereochemistry here, we're just going to switch the sign. Same rationale. The nitrogen is going to be first, the vinyl group is going to be second, and the methyl group is going to be third. If we trace that around, we go from 1 to 2 to 3, which is counterclockwise, which is S. But remember, we switched the stereochemistry. And so again, this is going to be an R molecule, right? The same thing applies. Give me a thumbs up if this is coming back to you. All right, good. All right, well, if Ernie thinks it works, then we should be good to go, right? Okay, let's do a couple more, and then we'll call it a day on the practice. The first thing to do is to sit down and do these now that you've got the hang of it. Who can tell me what the stereochemistry is in this this diether here? Thanks. Andrew says no. That's right. Perfect. No. Chiral. Centers. Nothing. Nothing is chiral in there. That's an achiral molecule. What else? I like the ones that are tougher. Let's try this one. Why don't we do this one, and then we'll call it a day, and then I'll let you get on your merry way practicing your spectroscopy. Okay, this molecule has one stereocenter. It's right here. All right. So we're going to start by drawing our hydrogen in the back, like that. The oxygen is going to be first priority. This will be last priority. Now we're going to analyze the two carbons. So this carbon is attached to oxygen, carbon, carbon. This one, remember, each bond to oxygen counts as a single bond to oxygen. So this one is attached to oxygen, oxygen, carbon, and there is our tiebreaker. And so this group is going to be second highest priority. This one will be third. We follow from 1 to 2 to 3, doing the dance around our stereocenter. We're going counterclockwise, and so the stereochemical designation here is S.